So this is a short lecture on material in section 4.6. So we're going to talk about approximating a nonlinear function like y equals x squared is nonlinear, or all the trig functions are nonlinear with a linear function. So a line is linear. And so the difference of y over the difference of x is always a constant. Okay, so let's just look at this. You kind of try to create this image to try to help. Um, so there you see I have the graph of y equals x cubed. That's the one. Well, I guess you can't really see the colors, but I think we can tell. We know what the graph of y equals x cubed looks like. It's that parabola shaped. And then we have the tangent line going through the point 2 comma 4, or 2 comma f of 2. And if we draw the tangent line for values of x close to 2 is maybe a good approximation to x squared. And it all depends on, you want to actually pretty close to you want to take values of x pretty close to where the tangent line intersects the graph. So in this case, where the tangent line goes through 2 comma f of 2. So let's say like 2.1 or 2.05. And the farther you get away, the worse the approximation is. And how good the approximation is just depends on how fast this curve goes up. So x squared doesn't go up as fast as x cubed. So the tangent line going through a tangent line for y equals x squared will give a better approximation than y equals x cubed for large values for values of x further away from the tangent point. Okay, so how do we get remember the slope of the tangent line? So we're just going to call L of x the tangent line through a comma f of a. And so what I'm saying there, L of x is a good approximation to f of x for values of x near a. So f prime of a is the derivative of f at point a. In this case, f of it is x squared, but whatever your function f is. So f prime of a is the slope of the tangent line, and then we take some point, and so then the rise over the run is the slope of the tangent line, right? So we're going to go so we go some value right here x. Um, we go a little bit further in this case to the right, and we get some point, take some point x that's near a, and so we know the difference of the x values is x minus a, and the difference of the y values is L of x minus f of a, right? So this height here, like here, that height is just f of a. In this case, a is 2, but that height there is f of a. This part of the triangle is L of x minus f of a. The horizontal part of that triangle is x minus a. And you take the rise over the run, and you get f prime of a. And that's what we have right here. So here we have this quotient right here. So f prime of a is that quotient, rise over run. And then we just solve for L of x. And so oh, that's my cat in the background. And so L of x is equal to f prime of a times, we just solve for L of x, and we get, it's f prime of a, sorry, f prime of a times x minus a plus f of a. Okay, and so we're going to use this fact. So let's see if we can use this isn't as practical as it used to be. So now that we have calculators and computers, this approximation, in terms of any kind of practical calculations, isn't really quite as important as it used to be. But let's just go through the notes. But there's some use to these approximations. And there's kind of, I think, an interesting example in these notes here. So these notes were given to me. So I kind of, I think there's some numbers I found hard to read. So I kind of circled it. Okay, so this is kind of like a similar picture, hand drawn to calculate basically this is just the equation of right here. That's just the same thing as what I just showed, and that's just the equation of the tangent line going through a comma f of a. And so again, the tangent line is a good approximation when x minus a is small. You get L of x is a good approximation to f of x. So let's just look at this one example right here. Okay, so let's say we have this function square root of 2x plus 1. So at x equals 4, okay, we know that f of 4 is 3. And okay, so we want to find the approximation to f of 4.2. So I'm saying now we have calculators, and so but there was a time you have people who didn't have calculators. I remember that actually. Okay, so we had slide rules, but you can do it with a slide rule too, but maybe just not as good. Okay, so okay, we're going to find the tangent line going through 4 comma 3. So f of 4 is 3, right? So right. Okay, so we're just going to find the equation. I think we're really very good at finding tangent lines by now. So you take the derivative of the function, and the derivative of the function is it's right here, right? You just use the chain rule. So you get 1 over the square root of 2x plus 1, and at 4 that the slope is 1/3. Okay, so here's your tangent line right here. Y minus 3 is 1/3 times the quantity x minus 4, and then you just solve for y. So now we're going to call it, instead of calling it y, we call it L of x. L means linear. So the linear approximation is 1/3 x minus 4 plus 3. Okay, so now let's just calculate L of, we want a value of f. We want to compute f of, we know that f of 4 is 3. And so now let's just compute what happens when x is 4.2. So what is it? That's like the square root of 9.4. And so we just plug 4.2 into, now this is easy to calculate, right? So before calculators, we could always calculate, these linear functions we could always calculate. Or, I mean, whoever was doing the calculation then, okay, so, and you get it's about, you get about 3 1/15, and that's about 9.4. Okay, so now let's do the same thing. Okay, so in this case, we just calculated f of 4.2, right? So we know f of 4, right? And so we want 0.2 units away, which is actually like 5% away. We went 5% away, which is actually kind of large, really. Okay, so now use your linear approximation to estimate the value of square root of 8.6. So in this case, yeah, what value of x do we have to plug into 2x plus 1 to take the square root of 8.6? So you solve 2x plus 1 equals 8.6, and you get, so we plug in x equals 3.8. So now we're going 0.2 units to the left. Yeah, so now we're going about 5% to the left. So I think a 5% difference is kind of, it really high. I think usually when you do these approximations, it's more like 1%, something super small. But anyway, we just plugged that 3.8 into our friend here, the approximation function, 1/3 times the quantity x plus 4 plus 3, and we get the square root of 8.6 is about 2 14/15. So okay, I might not have written it as what I guess they used to call this a proper fraction. So I'm not sure why. I would always write it as, unless we're told otherwise. I would have written this as, what is it, 44 over 15. Okay, but whatever. Okay, that's really not that crucial. Okay, so there's a few more problems in here like this, and there's lots of, there's always but basically that's the idea. You find for the first part of this lecture, you just find the tangent line, and the tangent line is a good approximation, tangent line through some point A, and near A, the tangent line is a good approximation to the nonlinear function. So linear is is a straight line, and nonlinear is any function whose graph is not a straight line. Okay, so here's maybe the more important point. So we're going to use differentials here, and we're going to, and there's a certain amount of hand waving here. So here we're going to say dx is about delta x, small change in x, and dy is this kind of small change in y. And if you ever take a more like rigorous math course, like your math major, you take an analysis course, you come with more rigorous definitions of dx and dy. Because we actually define, right, dy, dx, right? Remember, it's that limit as h goes to 0. Remember, a long time ago we learned this, f of x plus h minus f of x and all over h. And so we actually just use this as notation. We use this notation that looks like a fraction, dy over dx, but we never actually just said, dy and dx are, what are they independently? But anyway, but we're going to kind of pretend that it's a fraction where dx is a denominator and dy is a numerator. Okay, so okay, so we're going to measure the small change in x. So this is it's a faster way of doing it. Okay, so we know that dy dx is just another way of writing f prime of x. But this is something we kind of made up, right? We'll just use this notation that looks like a fraction, and then we'll multiply. See, this is where we multiply each side by dx. So what, we actually have, what does that mean, dx all by itself? We've never defined what dx is all by itself, but okay, I'm just being this kind of mathematician guy. Okay, anyway, so here we're going to say that dy is equal to f prime of x dx. I remember when I would teach Calc 1 as a graduate student, and I would write something like this, and one of the students would read, why can we do this? I go, well, we just start with this. And, of course, no one ever questioned me. So anyway, no one ever said, hey, well, what does dx mean all by itself? Okay, but anyway, I'll stop talking about that. Okay, but what's useful here is that we can think of dy as some small change in y, and dx is just a small change when we go from x to some like x plus h. Okay, so this allows us when dx is small, what's the small change in f of x? So dy is, what's the change from f of x when we go over we start at x and we go to some x plus h. What's the change in the y values, right? So what's the change? So we start here, we go over some dx. What is this small change dy? What is how far does that linear approximation go up? Okay, so let's just look at this example right here. So let's start with example 4. Then there's actually kind of I think a really fun example later on. Okay, so find dy so let's say you have y is 4x cubed plus 7x minus 3, and we take the derivative. So it's 12x squared plus 7, and so we say dy. Well, now we'll say that dy is 12x squared plus 7 times dx. Okay, so we move over some small change from x to, we go over dx units from x, and we go up dy units from y. Okay, so let's just maybe, okay, well there we didn't actually use it in any kind of application. So let's just use it, let's say for this square root function right here. So this is this example 5 right here. And okay, so find the value of dy given that x is 1 and dx is 0.01. Okay, so let's say if we start at 1, we know the square root of 1 is 1. Now, what's the difference between the square root of 1.1? So we're saying dx is 0.1. So what's the difference between the square root of 1.1 and the square root of 1? So here's our function, y equals square root of x. Okay, so now we use that differential form. Dy is equal to the derivative times dx. Okay, so now we're starting at, x equals 1, right? I'm trying to draw this freehand as I'm doing the lecture here. Yeah, so yes, we go there's our, I'm having a hard time drawing that point here. So let's say we're right here. I guess I'm not sure this drawing is really helping too much. Okay, but yeah, we start at 1, and then we're going to go over just 1.1 units to the right, and then what would this difference be? What is this? How far do we go up from 1? Okay, so if we go we start at 1, we go 0.1 units to the right. So now we're kind of approximating the how much did the square root function change? And so we just measure. So the square root of 1 over the square root of 1 is just 1. So we get 1/2 times 0.1, which is like 0.05 or about 1/20th. And so we're saying that the difference between the square root of 1, right? So it's saying that this difference between the square root of 1.1 and 1 is about 0.05. And I think in real life, if we can just use our calculators, the difference is really about 0.488. So it's not too far off. You have to add what, 0.01. Percentage-wise, it's not really that far off. Right. So, okay, so now let's go to the fun problem that I've been advertising. So it's like the grand finale of this video. So yeah, if you wanted to pause and I don't know, take an intermission. Okay, anyway. Okay, so okay, oh no, this isn't it. No, this is a good problem too, but let's go to the fun part. No, this isn't it. Oh, here it is. Here it is. Problem example 7. Okay, so this might be one of my favorite problems so far in the whole course. Anyway, a machine is designed to manufacture ball bearings, which I think is just some kind of like little metal round thing with a radius of 0.8 inches. But this machine, has some, it's not perfect. And so it's been measured, maybe someone, some people have taken samples and they've somehow measured the radius and they found the radius is off by about 0.05 inches. So the ball bearings are actually anywhere from 0.75 to 0.85 inches. It's kind of a percentage-wise, it's kind of a lot, I guess. So use differentials to estimate the range of volumes possible for a ball bearing manufactured by this machine. Okay, so one thing here is that this function v here, so here's the volume function. So notice here we see v in the parentheses 0.8. So basically it's saying that v is a function of r, and it's 4/3 this of r. It's just a function of one variable, and it's 4/3 pi r cubed. So we take the derivative, because when you take the derivative of the volume, you actually get the surface area of the volume. So let's use differential. So okay, so a small change in r times 4 pi r squared produces the small change in the volume. Okay, so let's say the radius is 0.8 inches. So this derivative part is 4 pi 0.8 squared. And now we're saying that the dr is either positive 0.05 or negative 0.05. And it's the same number, except you're just multiplying. The magnitude is the same. You're just multiplying by plus or minus. And so the change in the volume is about 0.128 pi inches cubed. Okay, so and if you actually put 0.8 in, right? So when r is exactly 0.8, right? You're going to get the volume. Again, this is like an approximate. No, I guess maybe it's not approximation. Oh no, it's an approximation. I think it's an approximation. You get about 0.683 pi inches cubed. So when you're exactly 0.8, you get about 0.683 pi inches cubed. And now we're saying is, okay, so let's say you increase the radius 0.05 inches or decrease it, so what we're going to do is here's the difference. So you have to add or subtract that 0.128 to, you add or subtract that to 0.683 inches. Okay, so the volumes are actually, so you're producing these ball bearings and the radiuses are, anywhere from 0.75 to 0.85 inches. Okay, so I mean, ideally they should be 0.8, but because maybe this machine isn't so great. And then so anyway, so the volumes, so you add 0.128 pi to the volume when the radius is exactly 0.8, and the volumes turn out to be 0.55 pi inches cubed, all the way up to 0.81 pi inches cubed. So that's actually huge. I mean, this is really a pretty big. I mean, those of you who are engineers would, I think you might say, I don't know, I don't want to put words in your mouth. That's really a pretty high percentage. I mean, it's almost, I don't know, it's not 20%. I mean, it's high. I mean, 0.128 over 0.683. So the problem is interesting. Like I say, this is a pretty bad machine, in my own humble opinion. Okay, anyway, so that's the end here. Anyway, that was, as I say, that's the end of this fun problem. And hopefully there are more fun problems to come.